In this video, we'll begin talking about the main topic of this module, which is recursion and recursive sequences. Recursion is an essential tool that anyone interested in computer science should master. The ability to understand definitions, concepts, algorithms, and etc. that are presented recursively, and the ability to put thoughts into a recursive framework are very useful skills to have. So we'll attempt to become more comfortable with that way of thinking. And then eventually we're going to discuss recurrence relations and how to solve them mathematically. So we'll remind you here the definition of the binomial coefficient that we already learned, and the notation, the parentheses with n sitting above k, and we read that as n choose k, or also we'll see capital C and then parentheses n comma k. We can define the binomial coefficient recursively. So assume that n is greater than or equal to 0, and that n is greater than or equal to k, which is greater than or equal to 0. We can define n choose k by first noting that n choose 0 is 1, and n choose n will be 1. This will be forming the basis for this definition. And then each n choose k, we can define it in terms of n choose 1, n minus 1 choose k, and n minus 1 choose k minus 1. So we'll say that n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. And in this way, we're defining each term in terms of previous terms. Now, there's a note here about definitions. When we state that something is the definition, strictly speaking, we should only define any term or object once. There should just be one definition. So in this case, since we've presented two definitions, what we mean is that these are completely equivalent definitions. They're interchangeable, and you can use either one as the definition. They are equivalent. So here's an example of applying this recursive definition. So we have 5 choose 2, and we want to compute this value. And we know that we can compute this value using factorials. This can be 5 factorial divided by 5 minus 2 factorial times 2 factorial, which is 5 factorial over 3 factorial times 2 factorial, and that's 5 times 4 divided by 2, which is 10. So this is a very nice computational formula that we can use. Let's see how we would apply the recursive definition. Well, since we know that n choose k should be equal to n minus 1 choose k plus n minus 1 choose k minus 1, that's our first step. We'll rewrite 5 choose 2 as 4 choose 2 plus 4 choose 1. And then in the next step, this 4 choose 2 will replace by this 3 choose 2 plus 3 choose 1. And this 4 choose 1 will replace by 3 choose 1 plus 3 choose 0. Now, our basic definition said that n choose 0 is 1. So in the next step, this n choose 0 is replaced by 1. And the 3 choose 1 plus 3 choose 1 we've rewritten as 2 times 3 choose 1. And then we keep repeating this process. Now we'll rewrite this 3 choose 2 as 2 choose 2 plus 2 choose 1. And the 2 times 3 choose 1, we'll rewrite it as 2 times 2 choose 1 plus 2 choose 0. Then again, we can replace this 2 times 2 choose 0 by 2 times 1. We can combine the like terms of 2 choose 1 plus 2 times 2 choose 1. And we can also replace 2 choose 2 by 1 because that was the other basic definition that we had. So we're using these two facts, that n choose 0 is 1 and n choose n is 1. Anytime that we get to an n choose 0 or an n choose n, we just go ahead and replace it by 1. And otherwise, we just keep breaking down the terms until we get everything in this form. So you can see we keep iterating through this process until in the end, every term that we have is of the form n choose n or n choose 0, and we get to replace them by 1s. So repeating this process, we eventually find out that 5 choose 2 is 10, which we know is correct. We computed that using the computational formula. So you might notice that it was quicker to use this computational formula, and that is true. But in terms of writing an algorithm, this will be much simpler to write. So it's not always that computing using the recursive definition is easier, but it helps us to understand the relationships between the objects, and when we're writing computer codes, it can often be much shorter to write a code this way using the recursive definition and then just let the computer run. Okay. Another thing that we can define recursively are polynomials. So let's first start with our usual definition of a polynomial that we know from algebra. If n is an integer greater than or equal to 0, then an nth degree polynomial in x is an expression of the form a sub n times x to the power n plus a sub n minus 1 times x to the power n minus 1 and plus dot dot dot, eventually plus a1 times x plus a sub 0, where these coefficients a sub n minus 1, and so on, are elements from some designated set of numbers called the set of coefficients. And the a sub n term should not be 0. The reason we require that is because we're claiming that it's an nth degree polynomial. So if the nth term had a coefficient of 0, then it would be a lower degree polynomial. And in our high school algebra classes, when we've worked with polynomials in the past, the set of coefficients was probably either real numbers or maybe rational numbers or maybe integers. So we're pretty used to seeing polynomials with integer coefficients that we can factor nicely. But this definition is just a little more general. It tells you that I could take any set of numbers and that could be the set of coefficients. We refer to x as a variable in the definition above, although more precisely, x is an indeterminate. There is a distinction between the term indeterminate and the term variable, but we don't really need to go into it here. A polynomial with 0 degrees, or a 0th degree polynomial, is called a constant polynomial, and these are simply elements of the set of coefficients. So we're quite used to seeing expressions like this one. F of n is equal to 4n cubed plus 2n squared minus 8n plus 9. This is a third degree polynomial, also called a cubic polynomial. And the drawback to this form of expression is that when we need to evaluate it, so let's say we want to find out f of 7, so we plug in n equal to 7, and these should be multiplications here. So in order to evaluate, we'd plug in 7 everywhere, and we have to cube 7 and then multiply it by 4, square 7, multiply by 2 and add them up, subtract 8 times 7, and so on. And eventually we find that f of 7 is 1,423. So if we're keeping track of how many operations we had to perform, we had to do 5 multiplications and 3 additions or subtractions. 7 cubed is a multiplication, and then 7 cubed times 4 is a second multiplication. 7 squared is a multiplication, and then 7 squared times 2 is another multiplication. So far we have 4. 8 times 7 is a multiplication. Those are your 5 multiplications, and then you'll see 1, 2, 3 addition or subtractions. So instead we could define a polynomial recursively. A 0th degree polynomial in x over a set of coefficients s is a non-zero element of the set. For n greater than or equal to 1, an nth degree polynomial in x over s is an expression of the form p of x times x plus a, where p of x is an n minus 1 degree polynomial. So essentially what this is saying is that recursively we can define the polynomial in terms of lower degree polynomial, products of lower degree polynomials. So for example, this one that we had, 4n cubed plus 2n squared minus 8n plus 9, we could equivalently write it as 4n plus 2 times n minus 8 times n plus 9, as you see here. So since it was a third degree polynomial, we can express it in terms of first a 1 degree polynomial that gets multiplied by another 1 degree polynomial, and so on. This form is going to be called the telescoping form, and you can imagine why it's called that, because we get these nested sets of parentheses that expand out. And we can always find this form of a polynomial. So here's another example. 5x to the fourth plus 12x cubed minus 6x squared plus x plus 6. That can be rewritten in this way. So 5x plus 12 is inside parentheses. Then we'll multiply that term by x. Then we'll subtract 6, and that's inside another set of parentheses. Whatever the result of that is, we're going to multiply it by another x, and then add 1. So you see we have a third set of parentheses. Once we find the result of that process, we'll multiply everything by x and add 6. So this is called Horner's method. And using this telescoping polynomial, if we wanted to plug in f of 7 as above, we needed only 3 multiplications, 3 additions or subtractions to compute the same value. So it's a little bit faster in terms of the computing power. Many computer languages will just represent polynomials as lists of coefficients. So for example, if the polynomial was minus x to the fifth plus 3x to the fourth plus 2x squared plus x, a computer program might represent this as -1, 3, 0, because I don't have a cubed term, then 2, 1, and 0 because I don't have a constant term. So here's an example of how we can use recursion in computer science. This will be called binary search. So consider a recursive algorithm for a binary search written within a sorted list of items. So let's say R is our sorted list of items, and R is R1, R2, all the way up to Rn. This is the set of items, and they're sorted. So for example, they give the example that each item might contain data of the buildings in a city, and the value might be the height of the building. Then R1 would be the tallest building, and we'll denote R1.key as its height. Then Rn would be the nth tallest building, and Rn.key would be its height. So a binary search algorithm can be applied to search for an item in the set R with a certain key value, meaning in this case with a certain height. And in order to do this, we would execute the algorithm by inputting 1 and n, because these are the first and the last items in our list. So I'm going to go through this algorithm and we'll talk about what it means. At the end of the process, the algorithm will basically spit out a value if it found the desired item, or it will spit out true if it found the desired key, or false if no such item exists in the list. So let's see what this says. So we'd start by saying we want to do a binary search of the set R with the indexes 1 through n. So basically what it's doing is it's going to look through the first half. So if j is less than k, we take the floor. The floor is, we round down to the nearest integer of j plus k over 2. So in this case, if j equals 1 and n equals k equals n, because we want to search through our whole list, 1 is going to be less than n for sure. So we're going to add 1 plus n and divide by 2. If that's an even number, if the sum is an even number, then we'll get an integer. But if it's an odd number, then we just round down. And then what does the algorithm do next? So then, because we know that this list is ordered, we can cut our data in half, and now we'll search through the other half. So if the middle of the data is equal to the value we were looking for, then the algorithm stops. Otherwise, if the value of the data is less than what we were looking for, then we'll search for the lower half of the data. Otherwise, if it was larger than the data we were looking for, then we'd search for the upper half of the data. So you kind of have this picture here where you can think about, we have this ordered list. This is the smallest value. This is the largest value. We're just going to go to the middle and we're going to ask, is this middle value smaller or larger than the one we're looking for? If it's larger than the one we're looking for, then we're going to repeat the process in this half of the data. If it's smaller than the one we're looking for, then we would repeat the process in this half of the data. And this algorithm is just going to repeat recursively, which means we're again going to chop half of the data in half and ask the same question. Now, if we're in the middle here, is the value we're looking for here, or is the value we're looking for here? So that's an example of how we're using recursive thinking in computing. The next two examples will be of recursively defined sequences. And we just want to make a note here, the notation that we're using. If a sequence is given the name, say, capital S, then the kth number of the sequence, we're probably used to seeing this S sub k notation, but we'll also be using this, what looks like a function, S of k. This notation is also perfectly valid. So it looks like in the next couple examples, we're going to be using the S sub k notation. So this example is called a geometric growth sequence. Define the sequence of numbers, capital B, starting with b sub 0 equal to 100 and b sub k equal to 1.08 times b sub k minus 1 for k greater than or equal to 1. So the rule says that each number in the list will be 1.08 times the previous number, with the starting number equal to 100. So you can see that to define this sequence, we only need to define the first term, and then all of the subsequent terms are just defined in terms of the preceding terms. So if I had a definition like this one, and then I wanted to find, say, the third term, then I can say B3, well, that by definition is equal to 1.08 times B2, but B2 by definition is equal to 1.08 times B1, so I replace that, but B1 by definition is equal to 1.08 times B0, and B0 I know is 100. So by proceeding through, I can eventually replace B0 by 100 and do the computation, and I find out that B3 should be 125.971. Another example of a recursively defined sequence is the Fibonacci sequence. The Fibonacci sequence is defined by, we give the first two terms, f of 0 is 1, f of 1 is 1, and then all of the subsequent terms, f sub k, are defined as the sum of the previous two terms. So f sub k is equal to f sub k minus 2 plus f sub k minus 1 for k greater than or equal to 2. So as in the previous one, if I wanted to find f sub 3, then I could just say, well, that's f sub 1 plus f sub 2. And f sub 2 I know is f sub 0 plus f sub 1. And these numbers I'm given, so that's 1 plus 1 plus 1, that's 3. So all of these examples were presented recursively, meaning that every object is described in one of two forms. One form is the simple definition, which is usually called the basis for the recursion. So the simple definition, the basis in this example, is just these first two, which are expressly defined. The second form is the recursive description, in which objects are described in terms of themselves with the following qualification. So these are, all of the rest of the terms are recursively defined. What is essential for a proper use of recursion is that the objects can be expressed in terms of the simpler objects, where simpler means closer to the basis. To avoid what might be considered a circular definition, the basis must be reached after a finite number of applications of the recursion. So to determine, for example, the fourth item in the Fibonacci sequence, I showed you the third one. But to find the fourth one, we would repeatedly apply the recursive rule. So just like I did above, we would say f4 is f2 plus f3, f2 can be replaced by f0 plus f1, f3 can be replaced by f1 plus f2, and then f1 plus f2, we have to replace f2 again by f0 plus f1. Once I've gotten everything in terms of f0 and f1, well, those were my expressly defined objects, so I know that they're both 1 and I can substitute in the ones. On the other hand, we could compute a term in the Fibonacci sequence by starting with the basis and moving forward. And so that's what you see here. We start with f2, we know is equal to f0 plus f1. That's 1 plus 1 is 2. Then f3 is equal to f1 plus f2. So 1 plus 2 is 3. And in this way, I'm sort of going up instead of coming down. So this will be called the iterative computation of the Fibonacci sequence. So we start with the basis and work forward to a less simple number. If we tried to compute using the recursive definition, it generally takes more time. The iterative computations usually tend to be faster. So a useful skill might be being able to convert back and forth between a recursive formula and a non-recursive formula, such as one that only requires iteration. An iterative formula is also more efficient than the recursive definition, but the recursive definition has its own merits, which I sort of touched on before, which is that it's usually very useful in manipulating algebraic expressions, especially those involving binomial coefficients. It also gives us insight into the interpretation. So for example, with the binomial coefficient n choose k, choosing k elements from a set 1 up to n, there are n minus 1 choose k ways of choosing k from the first n minus 1 elements, and there are n minus 1 choose k minus 1 ways of choosing the k elements if n is to be selected, and the remaining k minus 1 come from 1 to up to n minus 1. Then we'll apply the law of addition. So essentially, we're first counting all of the ways that we could choose the k not including the nth term. Then we're counting all of the ways that we could choose them including the nth term, and we're adding those two counts together. So it's insightful into what's going on behind the scenes to see it explained in one other way. So in the binary search algorithm that we discussed, the place where the recursion is used is clear. When an item is examined and the key is not the one you want, the search is cut down to a sublist of no more than half of the items that you were searching in before. So obviously this is a simpler search. The basis is hidden in the algorithm. The two cases that complete the search can be thought of as the basis. Either you find an item that you want, or the sublist that you have been left to search is empty when j is greater than k. The binary search algorithm can be translated without much difficulty into any language that allows recursive calls to its subprograms. The advantage to such a program is that its coding would be much shorter than a non-recursive program. In most cases, the recursive version will be slower and require more memory at the execution time, but it's simply easier to program. Just a brief blurb about induction. So we define the positive integers, and when we define them in terms of Peano's axioms, it's a recursive definition. The basis element is the number 1, and the recursion is that if n is a positive integer, then so is its successor. In this case, n is the simple object, and the recursion is of a forward type. The validity of an induction proof is based on our acceptance of this definition. So often when we're doing proofs related to recursion, we will use mathematical induction. So for any of the math majors in the course, you may or may not have already learned mathematical induction. I'll show you a little bit more later. This isn't going to be a huge part of this course, and you don't necessarily have to know how to do mathematical induction for this course. But if you are interested in reading more about the mathematics behind these things, reading about Peano's axioms and learning mathematical induction is a really great place to start. So here's an example of such an inductive proof. Proof of the formula for B. A formula for the sequence B, as in the example we saw above, is B is equal to 100 times 1.08 to the k. So we'll prove that by induction. When we do induction, we start with a first case. In this case, we want to use k equal to 0, and we can clearly demonstrate that this definition holds for our initial case. B equals 100 times 1.08 to the 0, which is 100, and that's the definition. so it's true. The next thing in an inductive proof is that we just assume that the same definition holds for some other integer that's larger than or equal to 1. And if it is true that it holds for some integer larger than or equal to 1, we just need to prove that it holds for the next one up as well. So let's examine b sub k plus 1. And we're working under the assumption that this formula is true for b sub k. So b sub k plus 1 should be equal to 1.08 times b sub k by the recursive definition. So we're working with our recursive definition. But by our assumption that bk is true, we can replace bk by 100 times 1.08 to the k. That's because of our assumption. And so then, by using the commutativity of the multiplication, we can rewrite this in terms of the desired formula, and hence claim that the formula is true for k plus 1. And that's all we need inductively to claim that, well, if we found out that it was true for some smallest natural number, in this case 0, and we found out that if it's true for any other natural number, then it's true for all of the ones that follow, well, that's enough to conclude that it's true for all natural numbers. And that is the idea of mathematical induction. So one other definition to be aware of is, what do we mean when we say the closed form of an expression? Let E be some expression involving variables, in this case x1 up to xn, which are allowed to take on values from some predetermined set. E is a closed form expression if there is a number t such that the evaluation of E with any allowed values of the variables will take no more than t operations. Now that's a little abstract, but let's see the next example. Reducing a summation to a closed form. The sum, E of n, equals, remember our sigma notation, the sum k is the index, it's running from 1 to n, and we're just adding up k. This is not a closed form expression because the number of additions needed to evaluate grows indefinitely with n. So a closed form expression would be n times n plus 1 over 2, which only requires 3 operations: addition, multiplication, then division. And this is a perfectly valid formula for adding up the first n many natural numbers. That sum is going to be equal to n times n plus 1 over 2. Okay, let's do some exercises together. So the first exercise, we're going to use our recursive definition of binomial coefficients to compute 7 choose 2. Remember, we have to continue to expand 7 choose 2 until we can define it only in terms of quantities defined in the basis. And what were those? That was that n choose 0 is 1 and n choose n is 1. So anything of the form a number choose 0 or a number choose itself, that's where we can stop and replace it by 1. Otherwise, we keep applying this recursive definition. Then finally, we'll check our result by applying the factorial definition. So 7 choose 2 is equal to 6 choose 2 plus 6 choose 1 by our recursive definition. Our recursive definition, I'll remind you, was n choose k is equal to n minus 1 choose k plus n minus 1 choose k minus 1. Now, 6 choose 2, I can write it as 5 choose 2 plus 5 choose 1. That's just this term. Plus 6 choose 1, I can write it as 5 choose 1 plus 5 choose 0. Now 5 choose 0, I can replace by 1. So this is going to end up being 5 choose 2. I have 5 choose 1 plus 5 choose 1, so I'm going to say that's 2 times 5 choose 1 plus 1. Now I'm going to replace 5 choose 2 by 4 choose 2 plus 4 choose 1. So again, that's just this much I've replaced. Then plus 2 times, and I'm going to replace 5 choose 1 by 4 choose 1 plus 4 choose 0. And I still have plus 1. So this is 4 choose 2. Then I have 4 choose 1 plus 2 times 4 choose 1, which is 3 times 4 choose 1. 4 choose 0, I'm going to replace by 1. This is 2 times 1, so this is plus 2 plus 1. Now again, substituting my recursive definition, this becomes 3 choose 2 plus 3 choose 1. That's just 4 choose 2. Then I'll have plus 3 times 3 choose 1 plus 3 choose 0. And then plus 3 if I add the 2 and the 1 together. So here I have 3 choose 2. Then I have 3 choose 1 plus 3 times 3 choose 1. That's plus 4 times 3 choose 1. Then I have 3 times 1, so plus 3 plus 3. Now 3 choose 2, I can replace this by 2 choose 2 plus 2 choose 1. And 3 choose 1, I can replace it by 2 choose 1 plus 2 choose 0. And I have plus 6 out here. My other basic element was n choose n. So now I'm at a point where I can replace this by 1. Then I have 2 choose 1 plus 4 times 2 choose 1. So I have 5 times 2 choose 1. Then I have 4 times, I'm going to replace 2 choose 0 by 1. So this is plus 4 plus 1, plus 6 rather, from here. So this is 11 if I add 1 plus 4 plus 6. 11 plus 5 times, and I'm going to do this one more time. This is going to be 1 choose 1 plus 1 choose 0. And now these are both basic elements, so I can replace them each by 1. So this becomes 11 plus 5 times 1 plus 1, which is 5 times 2 is 10, 21. So all of this I needed to compute recursively 7 choose 2. And then I'm told that I should double check my answer with the factorial definition. So 7 choose 2, that should be 7 factorial over 7 minus 2 factorial times 2 factorial, which is 7 factorial over 5 factorial times 2 factorial. And we know that I'm going to get a lot of cancellations here. 7 factorial is just the first 7 integers all multiplied. 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. Then if I start canceling, I get, this is 7 times 6 is 42. 2 times 1 is 2. That's 21. So we can see that we did the recursive computation correctly, and it was obviously quite a bit longer, but in terms of perhaps writing an algorithm for something like this might be a simpler thing to code. At the very least, it shows you these fascinating relationships between the binomial coefficients. And if we needed to do an algebraic manipulation, that would come in very handy. Okay, next, we'll define the sequence capital L by L sub 0 equals 5. So this is our basic element that's expressly defined. And then for k greater than or equal to 1, L sub k is 2 times L sub k minus 1 minus 7. So these are the rest of the terms defined recursively in terms of the first. Determine L sub 4 and prove by induction this formula. So let's start with L sub 4. I'm going to work up iteratively. So I'm going to say I know L sub 0. So let me find L sub 1. That should be 2 times L sub 0 minus 7, according to my recursive definition, which is 2 times 5 minus 7, which is 10 minus 7, which is 3. Then L sub 2 is 2 times L sub 1 minus 7, which is 2 times 3 minus 7, which is 6 minus 7, that's negative 1. L sub 3 then should be 2 times L sub 2 minus 7, which is 2 times negative 1 minus 7, which is minus 2 minus 7, and that's negative 9. And L sub 4 is 2 times L sub 3 minus 7, which is 2 times negative 9 minus 7, which is minus 18 minus 7, and that's negative 25. So I found L sub 4. Then the question asks me to prove by induction the formula L sub k is equal to 7 minus 2 to the power k plus 1. So I need to start with my first case. I'll say, I'm going to give this proposition a name. I'm going to say the proposition is P. So let P of k be the proposition that L sub k is equal to 7 minus 2 to the k plus 1. Then I want to start by investigating the proposition evaluated at 1. So I'm going to use LHS for left-hand side. Left-hand side of P1, well, that's equal to L1, which by my recursive definition is 2 times L sub 0 minus 7, 2 times 5 minus 7, 10 minus 7 is 3, as we already know, and 3 is equal to 7 minus 2 squared, and that's equal to 7 minus 2 to the 1 plus 1. Well, that's exactly what I want it to be, so that's the right-hand side. So I'm going to say my first case is verified. Now I want to assume that P of k is true for some k greater than or equal to 1, some natural number larger than or equal to 1. That is, I want to assume L sub k is equal to 7 minus 2 to the k plus 1 for some k greater than or equal to 1. Now let's see pk plus 1. I want to show that if it's true for any k greater than or equal to 1, then it's true for the subsequent k. And so if it's true for each natural number after a natural number, then we can just assume that it's true for all natural numbers. So the left-hand side of pk plus 1, by my recursive definition, is 2 times L sub k minus 7. And by my assumption, L sub k has this form. So I'm going to replace L sub k in my recursive expression by this form that I'm trying to legitimize. So it's 2 times 7 minus 2 to the k plus 1 minus 7. Now I'll just distribute. 2 times 7 is 14. 2 times minus 2 to the k plus 1 is minus 2 times 2 to the k plus 1, and minus 7. Well, 14 minus 7, I can combine these like terms. That's going to be 7. And then 2 times 2 to the k plus 1 is minus 2 to the k plus 2. And I can write that as 7 minus 2 to the k plus 1 plus 1, which is the exact form that I wanted it to have. So that's equal to the right-hand side that I wanted to see, and I've verified it. So finally I'll say hence, by the principle of mathematical induction, pk is true for all k and n, for all natural numbers. I'm going to go ahead and say except for 0, because we didn't verify that. So again, I just want to pause here and say, if you are a mathematics major and you haven't taken a proofs course yet, you will learn this in your proofs course. We did some logic in this course, and we learned a few proof techniques, but mathematical induction is not one that you have to know. If you're not a mathematics major and you don't have to take a proofs course, then you may never learn the mathematical induction, but it is a beautiful proof technique, and it's closely related to the idea of recursion. So even if you are a computer scientist, it's something I would recommend that you read up on. Okay, next exercise. We have a polynomial. P of x equals x to the power 5 plus 3x to the power 4 minus 15x cubed plus x minus 10. First, we're asked to write this polynomial in the telescoping form. So I can see that the leading term, x to the power 5th, the coefficient is 1. So I'm going to write x. And then the next term, x to the power 4, the coefficient is 3, so I'm going to say x plus 3. And then put that in parentheses, and that's going to get multiplied by another x. The next term, the x to the power 3 term, has coefficient minus 15, so I'm going to write minus 15 and close the parentheses. And then I'll see that I'm going to write x again, but I don't have a squared term. So essentially what I would write here is plus 0 because the coefficient of the squared term is 0. Then close my parenthesis. Again, put my x. The coefficient of the x to the power 1 term is 1, so I put plus 1, close my parentheses, and put x. And then the coefficient of the constant term is minus 10. And that's the last coefficient, so I'm done. So the only thing that I didn't really have to do here is I didn't really have to write this plus 0, but I wrote it just to show you how I am doing this process. So this ends up being x plus 3, x minus 15, x plus 1, x minus 10. So that's the telescoping form of the polynomial. And if I wasn't sure if I did it right, I could go ahead and multiply this back out. I could say, okay, x plus 3 times x is going to be x squared plus 3x, and then minus 15. And then the next step, multiply the x in here. I get x cubed plus 3x squared minus 15x. Then multiply in one more x. I'd have x to the power 4 plus 3x cubed minus 15x squared plus 1. And then finally multiply in the last x to the power 5 plus 3x to the power 4 minus 15x to the power 3 plus x minus 10. And that's exactly the polynomial I started with. So I know that I have done it correctly, and you can see I started from the inside and I worked my way out. Part B asks me to use a calculator to compute P of 3. I'm just going to go ahead and compute it using the original form. So this is going to be 3 to the power 5 plus 3 times 3 to the power 4 minus 15 times 3 cubed plus 3 minus 10, which is 243 plus 243 minus 15 times 27 is 405. And then minus 7 if I combine 3 and negative 10. And this ends up being 486 minus 412, which is 74. Now use the calculator to compute P of 3 using the telescoping form. Again, we don't really need a calculator for these simple multiplications. So plugging it into the telescoping form, that should look like 3 plus 3 times 3 minus 15 times 3, 3 plus 1, 3 minus 10. So working my way from the outside in, this ends up being 6 times 3 is 18 minus 15 times 3. So then 18 minus 15 is 3. 3 times 3 is 9. 9 times 3 is 27. This becomes 28 times 3, which is 84, minus 10, and that's 74. So in terms of the calculations, using the telescoping polynomial, not only did I do fewer multiplications, but I actually had smaller numbers as well. The largest number that I ever had was I had to do 28 times 3, which was 84. You can see in the above calculations, I had 3 to the power 5 is 243. And then I added those up, I got 486. So I'm dealing with these larger numbers, not as easy to work with, and on top of that I'm having to do more operations, more multiplications, and more additions and subtractions. So the final question is compare your speeds in part B and C using the telescoping polynomial is faster. All right. Now finally we have what is wrong with the following definition of a function f from the real numbers to the real numbers. So we have f of 0 equals 1, and we have f of x equals f of x divided by 2 if x is not equal to 0. So we have sort of like this first term, this expressly defined first term, and then this recursively defined term for all of the other terms. And the problem is asking us what is wrong with the definition. Well, this definition is only good for x not equal to 0, but the express definition that we were given is only good for x equals 0. So for example, if I wanted to find f of 1, I would have, this is f of 1/2 divided by 2. But I wasn't given f of 1/2, so I could try to find f of 1/2. That should be f of 1/4 divided by 2. But again, I wasn't given 1/4, so I could keep looking. And the problem is that I will never get to 0 this way, because I can keep cutting in half, 1/2, 1/4, 1/8, 1/16, on and on and on and on, infinitely many times, and I will never get to f of 0 in this place. And f of 0 is the only term that I know the definition for. So essentially, this process does not terminate after finitely many steps. So this is not a valid recursive definition, because I never will get to where I can use the information that I was given. So that is the last exercise in the lecture note, and it's a very important exercise and very interesting. So definitely something to think about, and something to make sure that if you are trying to define something recursively, you want to check that it is a valid definition that would be helpful to someone to use. So we'll end this video here for now, and then we'll continue in the next lecture.